Hey everybody, this is Alex from Merced, and welcome to another episode of Data Nation. And today I want to just talk about something I was thinking about, sort of like the architectural reasons for why Apache Iceberg is able to offer a feature called Partition Evolution, where you can actually change how the table is partitioned without the need to rewrite the table, and then lose all the metadata history and whatnot, versus Delta Lake, which allows schema evolution but doesn't enable partition evolution. So you can't change the partitioning scheme without rewriting essentially the entire table's metadata history, and possibly even the data files. So why is this? And to understand the why, you have to understand the difference in architecture. And again, it's the underlying architecture is one of the main reasons why I generally am personally a Apache Iceberg advocate. One, the ecosystem, and two, the architecture, because there's a fundamental difference that allows this. So first, let's take a look at how Apache Iceberg does it. So we can understand sort of then why Delta Lake's architecture basically precludes the ability to do this without some sort of fundamental change to how Delta Lake works. So Apache Iceberg, how the table is partitioned isn't defined in the snapshots. So basically, as the table changes, the actual snapshot information doesn't contain the information of how the table, what is the table schema, what is the table's partitioning. This is a fundamental thing. So, because again, there's three files in Apache Iceberg. There is metadata.json, there's a manifest list, that's the snapshot, and then there's the manifest, the groups of individual files. So, in the manifest list and manifest, the stuff that actually defines sort of, hey, what files make up this snapshot, those things don't actually directly detail, hey, what is the partitioning scheme or what is the schema. Instead, what they do is they generally have an ID of which schema was that particular file or manifest written with, and which partitioning scheme was the active scheme sort of when it was written. So it usually have an ID like 1, 2, 3. So how do I know, hey, which is partitioning scheme 1 and which is partitioning scheme 2? That's on the metadata.json. And essentially in the metadata.json, which is the file that you read before you do anything else, it has a list of all the schemas historically for that table and all the partitioning schemes for that table. So basically at the beginning of the reading process for the table, the engine is already aware of not just the current schema, but of all the previous schemas, not just aware of the partitioning scheme, but of all the previous partitioning schemes, because those are in a file that they're going to read before they start assessing and doing like file skipping and saying, hey, let me skip this file or that file. So because of that, what happens is that it can identify and understand, hey, this file was written with this partitioning scheme, or this group of files, this manifest was written with these partitioning schemes, and these ones were with that, to evaluate them differently and be able to apply multiple different types of partitioning schemes in its process of sort of eliminating files and manifests from, hey, what is the things I want to scan? Because again, all that historical information is provided up front, because all that data isn't sort of in the history, it's always kind of centralized in that metadata.json, and that's why a new metadata.json gets written every time you make a change to the table. Now, in contrast, the way Delta Lake works is that these kind of details are tracked throughout the history. So basically what will happen is like the very first transaction or the very first log file will have things like the table's partitioning scheme and initial schema and things like that. But the problem is the partitioning scheme cannot really, basically the way you're going to prune files in Delta Lake is you do it as you go. So for example, as you go through these Delta log files, and again, these Delta log files are the things that capture the changes to which files are part of the table, kind of like Git commit history, where it's like plus lines of code, minus lines of code. So essentially I'll go to the next Delta log file and it'll add certain files and maybe subtract certain files. So essentially, if I'm the engine, the way I would evaluate it is I know what the partitioning scheme is. I know what my query is. So then I know, so as I go to the next Delta log file and say, hey, these 10 files are added, I would do the pruning right there and then. I'd say, okay, hey, these files have partition values that are relevant. These files don't have partition values that are relevant. And I would prune it right there. So let's say I get down to, I'm 10 log files in, If the partitioning scheme were to change, well, then chances are the way I've evaluated all the files up to this point may change. Okay, so then what happens is that I theoretically would have to kind of go all the way back and start over. Okay, and that's sort of the fundamental problem. Like, basically, there's information that I won't know until I get to that point in the history that would affect decisions I have already made up to this point. Okay, so again, because of sort of like the way you're going to read these delta log files and the way they're evaluated, it does kind of preclude the possibility of partition evolution. Yes. Okay. And then now again, your schema can evolve. Why? Because what the schema isn't going to involve what files are pruned from scanning. So in that case, you can change the schema from delta log file to delta log file, and it doesn't necessarily invalidate any of the pruning work you've done in the past. It's just going to affect how the engine superimposes the schema when it provides you the output. Okay, and now that I'm starting to think about this a lot, I'm trying to think through okay, what would happen if you did, let's say, evolve a partition. So let's say, hey, you get 10 log files in. Does that invalidate truly invalidate what's happened before? Theoretically, assuming that all files going forward, the problem is you're not grouping the files into manifests. Essentially just the way that the metadata is tracked from log file to log file sort of makes it kind of hard to kind of switch how you're partitioning midway through once you get past that sort of initial understanding of the table. Because, again, you're not tracking, unlike, there isn't a separate file that tracks the history of schemas and the history of partitioning like there is in Apache Iceberg. Instead, again, it's captured throughout the changes to the table. Each log file is not only capturing additional files and subtracted files, but also changes to the schema. So in that case, again, these are things like I'm reading log file 1. I'm unaware of changes to the table structure that might occur later on at a later log file, which is fine for most types of table evolution. But again, table changes in table evolution that might affect the way I prune files, that becomes a little bit more tricky. So again, it's a fundamental architectural challenge, and a fundamental distinction in how the two formats are architected that allow one to have this feature and the other one to not. Okay, because by decoupling history from the understanding of the structure of the table, Iceberg has that flexibility. Well, in Delta Lake, it's essentially its metadata format is actually pretty straightforward when you really think about it. It's I go to one file, these files are added, these files are subtracted. Okay, the schema's changed in this way, and then I just kind of keep building up the table as I go along until I get to the current snapshot. And hey, I've reconstructed the table very much like when you switch branches in Git, where it starts from the initial commit, adds and subtracts lines of code until it gets to the current head of the branch you switch to reconstruct the files at that point, or basically probably starts at the earliest shared commit when you're switching branches in Git, because why would you reconstruct what you already know? But yeah, so that's something to kind of think about. So again, there are distinctions in the features between the formats that really matter because they're architectural decisions that were made and how the format works that preclude, being able to do certain things and exclude being able to do certain things. So hopefully you found that interesting. Again, what is the benefit of being able to evolve partitions? Being able to change how your table is partitioned without having to rewrite the table. Again, when you think of petabyte-sized tables where you might want to change your date-time type of partitioning as the velocity of the data grows, that can be a pretty useful thing to have. Okay, and rewriting tables can be really expensive. Is that the only thing to consider? No, there's plenty of other things to consider. Again, services built around these formats. Okay, so there's the core feature set that these formats have, but then there's the services. So in the case of Delta Lake, that's going to be really tied into what Databricks offers users of Delta Lake. While in Iceberg, then that depends on the ecosystem. And again, the beauty of that is in the ecosystem, you'll have multiple options on who optimizes your tables, who can do your cleanup, who can automate certain things and provide certain services to you. While in Delta Lake, while you have a lot of people who can read and write to Delta Lake, there's not as many providers of sort of management services for your lakehouse. and that now I'm starting to get kind of off the topic of this particular episode. I've talked about this before, but again, these are just sort of like distinctions. But again, there are architectural reasons, sort of why certain features are done the way they are. There's also some really interesting differences because two features that are also very similar or considered similar, that are architecturally very different and have different implications, are hidden partitioning in Iceberg versus generated columns in Delta Lake. Now, the difference being is that in Apache Iceberg, hidden partitioning, basically allowing you to track partitions based on the transformed value of a column, basically precludes the idea of having to store an additional column in your Parquet files. Okay, so when you're actually going to store less data because you're not storing this additional column with a partition value, instead the metadata tracks the transformation, the partitioning scheme, which would say, hey, this table is partitioned based on this type of transformation. We'll say a month transformation on this column. So then it can just do that transformation based on the ranges, the value ranges for that column that it has in the metadata. Okay, so basically that processing can be done strictly from the metadata, and any engine can really kind of just do those computations. Okay, it's not really dependent on some sort of external compute source, because again, how that transformation is tracked in the metadata, and it doesn't have to be physically stored in the individual data files in order to partition that data. While in Delta Lake, they have the generated columns feature, which I think is still only really workable. Maybe it's usable in Spark now, Spark open source, but I think last I checked is really still pretty much mostly just a Databricks feature. Because essentially the way generated columns works is, I don't think the actual like generated column like formula or like what that relationship is stored in the metadata. I might be wrong on that, so don't quote me on that one specifically. But it's something that's more stored in the compute system. So in the sense that like Databricks knows that, hey, this column is generated by the values in this column based on X function, and so that way it can automatically generate those values when you add data, and then automatically add predicates if you partition based on that generated column. Okay, so basically that more extra level of partitioning isn't necessarily tracked. You're still essentially saying, hey, I'm partitioning based on this extra column, and that extra column is being physically stored in your Parquet files. It's just more like that the compute engine is able to kind of give you some extra niceties because it's built to work with the format that way. Okay, and then this is sort of the nuance of a lot of Delta Lake features, where they're not necessarily actually features of the metadata. They're not like things that are stored in the metadata, or benefits that the metadata kind of tracks that other engines can take advantage of. They're oftentimes features you get for using the format in the Databricks platform. And oftentimes that can get really kind of confusing to track when is what in what category. Okay, and again, point being is that because Iceberg really focuses on making sure that any of its features are metadata enabled, it makes it easier for multiple tools and for it to be more tool agnostic in you being able to take advantage of those features. Okay, so again, architectural differences. So I'm going to leave it at that for this episode, but hopefully that gets the brain tickling and thinking about these formats. This is, I spent a lot of time thinking about this and reading about this. I'm not going to tell you that I know every single sort of step that every query engine and every platform does in reading these, in understanding and working with this metadata. But I think I'm pretty sure, I feel pretty confident in the way that I explained it in this episode is generally pretty accurate. It's one of those things to try out yourself. You can go and investigate a little bit more yourself. You'll find that you'll probably end up to the same conclusions that I've come to. Taking a look at the documentation, taking a look at the specifications for these formats, taking a look at how these engines interact with these formats. Have a great day and enjoy. I'll see y'all later.